My name is Suby Raman. I'm an engineer at Duo Security based out of Michigan in the United States. And we've been doing some of the earliest explorations of the Web Authentication API. And in a few weeks, we will be rolling out passwordless authentication to the millions of users who depend on us for secure access to their applications. This is our preview with our integration with Windows Hello, which is the biometric authenticator that comes built into Windows 10. I'll go ahead and play this video here. OK, that happened really fast, but that's the cool thing. The Duo website summoned Windows Hello. My face was recognized with Windows Hello, which logs me into Duo. This is really cool. For the first time, a website can now recognize my face to log me in, which is just amazing to me. But before I talk about WebAuthn, go into samples, talk about how you register and authenticate with WebAuthn, I want to talk about this. This is a password. This was my first password. I had a high opinion of myself. But I want to talk about passwords because I feel we need to fully understand them to understand why we might want to replace them with something better. It's almost every day that you see a news article that looks something like this. I imagine it's happened to many of us. You receive an email saying, oh no, change your password, we messed up, it's on the internet, my bad. But once your password is gone, that's basically it. Unless you're one of the uncommon few with two-factor authentication set up, a hacker can basically totally impersonate you. And it's kind of crazy because a password is really all that stands between a hacker, your sensitive data, medical records, bank records, more. Because I think it's a really sad situation. Even if we do our best to follow security best practices, it can still feel a little hopeless because our data is out there, it's in a sad cloud, and our passwords are at constant risk of theft. But how did we get here to the point where we constantly have to worry about breaches? Well, let's go back in time. Let's go all the way back to ancient Rome. There was this dude on the right. He was called a tesserarius. He was responsible for maintaining and changing the passwords that granted access to a military camp. This worked well for a few reasons. You saw all the people who the password was being distributed to, so you had good indicators about who to trust. Also, the password was changed out every night, so password staleness and reuse was less of a risk. And this worked pretty well for Rome for a while, until it didn't. That didn't actually happen, but it would have been kind of funny if it did. But let's flash forward to the 1960s. MIT now has significant computing resources, but they've developed a problem. Multiple people are logging into the same mainframe. So people are meddling in each other's files. They want to be sure that people aren't using more computing time than they should. So what is the solution here? Well, this researcher, Fernando Corbato, decided to implement a simple password authentication scheme. You would input a username and a password, and you would get access to your files. The computer would kick you out when you're done. This was a pretty reasonable solution at the time. Everyone at MIT generally knew each other, trusted each other. All he wanted to do was deter pretty harmless meddling in each other's business. But from the outset, this actually didn't work all that well. People guessed each other's passwords really easily. Fernando himself wrote down all of his passwords in a crib sheet, which is absolutely what you're not supposed to do. At one point, the master password was even leaked. So the first implementations of passwords really did not go all that well. But in the 1980s, the idea of accessing networked resources over a public medium starts to hit the masses. And with Prodigy and America Online, passwords were the existing way of doing things, accessing resources over a network. And so it was bolted onto the internet. And that's the system we've been saddled with. And I believe we've had problems ever since then. I'm going to go over 5 specific problems that I think are important to talk about when we think about passwords. The first is that passwords represent a shared secret. This is fundamental to the concept of passwords, and it has far-reaching implications. The password is the fundamental way that you prove your identity to a system that doesn't trust you. In other words, if a hacker gets your password, they have the full ability to impersonate you. So this is my cat, Zeus. He wants to register on my website, so he sends me a password. I'm the sad cloud represented on the right there. I have to store that password in a database in order to authenticate Zeus for future authentications. Let's say Darth Vader comes along, and in addition to ruling the galaxy with an iron fist, he really has it out for my cat. So he can get my cat's password. He can go straight to the database. If the password is stored in plain text, he can get it from there. He could also potentially get the password in transit. If the password is not submitted over TLS, he can just read the traffic and grab it. There's nothing about a password submission that ensures it's being submitted over an encrypted channel. Now Darth Vader has the ability to fully impersonate my cat, and that makes him super evil and rude. This is a real problem because the password is the primary way to verify our identity. It means that hackers have an easy way to impersonate us. The second problem, passwords are hard to create and remember. According to recommended password hygiene, we're supposed to create random, long passwords. This increases entropy, makes it harder to guess. Does this actually happen in reality? No, of course it doesn't. These are some of the most common passwords. Most of us don't have time for this. Realistically, the human brain is only so good at generating long, random strings. I love that people are thinking about monkeys and Star Wars when they register for websites. The earliest internet worm actually used this weakness. You can use a simple dictionary of common passwords to break into common systems. This is the C code on the right that was like just trying out passwords using a dictionary. This spread all over the internet and caused $10 million of damage before it was contained. Problem 3. Passwords are easily stolen. It's so easy. I know because I helped build a phishing assessment tool called Duo Insight. This has sent hundreds of thousands of fake phishing emails to help organizations assess their risk to phishing attacks. You can see you can craft an email here on the right. It looks like a fairly convincing Google Docs email. And it'll send you to a page that looks like this, which looks like, a Google login page. But if you look at the URL, you will notice that it is not Google at all. It is something portal.login-online.com, which, are you really going to notice that? Maybe, but probably not, because the site looks convincing. It has all the visual indicators that tells you that it's Google. This is what makes phishing attacks so effective. What we found is that 31% of users click on phishing links, and around 17% of users will submit their passwords to phishing sites. So I want to recognize the gravity of this. Imagine that you're an activist in a country and your government is spending millions of dollars to steal your passwords. If they get access to your email account or your Dropbox, that could compromise you and dozens of people around you and subject you to persecution. The risks are really grave here, and they're very important to recognize. In America, of course, I think we are familiar with the phishing attack that occurred in 2016 of the Clinton campaign by Russian hackers. Some people have openly wondered in America if we didn't have passwords, perhaps we have a different president. Problem 4, passwords encourage unsafe reuse. How many people here reuse a password? Everyone get your hands up, I know you do. So something like 80–90% of people will reuse passwords. For the reasons I mentioned, they're annoying to remember, they're annoying to create, we can only stuff so much into our heads. The recommended thing is to use a password management tool. Most people aren't going to do this because it's another thing that gets in the way between you and your stuff. Problem 5, passwords as developers are hard to secure. So let's say we receive a password during registration. What happens then? Well, we have to store it. But you can't store it in plain text because Darth Vader can just break in and steal it. So you have to hash it, a one-way function that scrambles it. But, oh wait, there are dictionaries with commonly hashed passwords. Some algorithms are insecure, so you have to add a random bit of data called a salt in there. And you know what? That's still not enough. Because even at the smartest companies in the world, all it takes is a single piece of misconfigured software hiding somewhere in a massive software architecture, and the passwords are leaked. And again, these are some of the smartest security minds. And if they haven't got it perfectly right, what chance do we have? So 40 years later, Dr. Corbateau gave his verdict on internet passwords. Unfortunately, it's become kind of a nightmare. And I think our instinct as developers might be to blame humans, like, our users, why can't they just remember random passwords? And, they're so dumb, why are they reusing passwords? They're losing passwords, all of us, we are so dumb, why can't we just do the right thing, right? I think this is the wrong impulse. If these problems keep happening, it's not a human failing. It's the fact that passwords have not evolved to meet the needs of the modern internet, where users and systems are not supposed to trust each other. This is not ancient Rome, where you saw the people who the passwords were being distributed to. This is not MIT, where you knew everyone. I don't know you, and I don't trust you. That's the internet. In other words, I think that passwords represent one of the greatest user experience challenges of our time, and it's a challenge that we all have to face and we all have to meet. So I've talked about some of the problems, and now I can move on to talking about web authentication. How does web authentication solve these problems? Web authentication allows us to authenticate our users using public key cryptography. This is a spec that has been developed in a partnership with major vendors like Microsoft, Mozilla, Google, others. It's great because we finally have major backing for a new type of authentication scheme to make WebAuthn succeed. However, some of you might be unfamiliar with public key cryptography, so I'll give a brief overview of how it works. Remember, I talked about this, how passwords represent a shared secret. If Darth Vader steals it in transit or from the database, he can impersonate my cat. Now, let's say instead there are two keys, a private key and a public key. The private key stays with my cat in his litter box, not in his litter box, that's gross, somewhere else, but on his device, it doesn't leave. The public key can be sent to the server, it can be stored in the database, and it is useless without the private key. The important thing here is that the combination of the two keys is what is used to authenticate me. In other words, there's no shared secret. The public key by itself is not useful. So let's say that Darth Vader attempts to get the public key from in transit or in the database. There's nothing he can really do. If he runs away with it, he can't do anything with it, and he definitely can impersonate me. This is the promise of authentication with public key cryptography. It's a way to identify and authenticate users across the internet without passwords. This idea has been around for some time. This is an article from 1997, which proposed using client certificates to authenticate users with public keys. Obviously, it didn't happen for complexity and computation reasons, but I love that it describes it as a hitherto esoteric realm, which we are finally able to enter. Many of us are already doing this. You've probably and perhaps uploaded public keys to GitHub, which allows us to authenticate over SSH without passwords. Web authentication is broadly similar to this. A major perk of web authentication is that it can integrate with authenticators that are now directly built into your devices. I see some MacBooks in the audience which have Touch ID on them. This is exciting to me primarily for accessibility reasons. Our users who are memory impaired or have mobility problems might have difficulty with passwords, but may have a better experience with a biometric authenticator. So before I go into code samples and so on, I want to just define some terms. An authenticator is the hardware that the user interacts with for registering and authenticating. You can think about Touch ID, Windows Hello, a portable authenticator like a YubiKey. A credential is a private-public key pair that is used for authenticating. A relying party, this is a term used in different security contexts. It means that the entity or organization responsible for registering and authenticating users. So at a high level, we describe web authentication with three characteristics: as strong, as scoped, and attested. When I say strong, I don't really mean that you can use a biometric authenticator. That's something cool. What I mean is that on many of our devices built in today, we have entirely separate computers, secure hardware for cryptographic operations. The iPhone calls this a secure enclave. Windows calls this a trusted platform module. This is really cool because a weakness of public key cryptography is that the private key can be stolen. This makes it really, really hard, if not impossible, to do so. Scoped. Scoping is an important way to protect against many common types of phishing attacks. So an important property of web authentication is that a credential, the public-private key pair, can only be used at a specific origin. So say, for example, https fullstackfest.com. So this works like a browser cookie. If my cat has registered a credential at this origin with this credential ID, the authenticator will do a check to see if that credential has been registered at that origin. If it has been, it'll let him through. Now, let's say that Darth Vader has redirected my cat to https evil-fullstackfest.com. This is a site that impersonates the original site, maybe for the purposes of getting data from him. So if he attempts to authenticate with that credential, the authenticator does an origin check and says, no, this is a phishing attempt. I'm not going to let you through. This helps mitigate against many of the common phishing types I alluded to earlier. Attestation, this is another A word. It can be a tricky concept to understand, but what it basically does is it allows us to prove cryptographically that a key pair came from secure hardware. So let's say, for example, that Darth Vader has taken over your phone, and he's manufacturing fraudulent key pairs that he can take off of the phone. We need some way to prove that the key pairs are coming from secure hardware in a place that Darth Vader cannot access. The way that broadly works is that a certificate is burned into an authenticator, and it's sent along with the registration event. And if it checks out, the registration can proceed. If Darth Vader has altered the phone, we can reject the registration and tell him to screw off. So now we can look at code. So registration. This is where the user creates a key pair and gives us the public key. At a high level, it works like this. The server requests the user to create a new key pair. That happens, a public-private key pair is created, and the public key is sent to the server for storage for future authentications. So this is actually a huge step forward because if an authenticator like Windows Hello or Touch ID is generating the credentials, it means the user is no longer responsible for generating random secure passwords, which is awesome. The Web Authentication API on the front-end side is actually pretty simple. There are two important functions provided, one for authentication and one for registration. To create a new key pair, you call navigator credentials.create with an object I'll talk about in a second. I want to first point out this await keyword. All functions in the API return promises that you have to wait on. This is for a few important reasons. The first is for privacy reasons. You can't register or authenticate a user without their explicit consent. This can be tapping a security key, them putting their fingerprints on the fingerprint reader, and so on. The second is that this allows time for the user to pair an authenticator they might have on their body over Bluetooth or NFC. So this is what the UI experience looks like. The website will show something like this during registration. The API summons Windows Hello to verify the user to create the credential. After that's finished, the user waits for the server to verify all the data, and then we are finished. So now we can talk about the configuration you can pass into this function. This is actually the minimal configuration required, and there's a lot more you can do here. First, the challenge. This is a cryptographically random series of bytes that are generated on the server. It's used to prevent something called a replay attack, where Darth Vader, if he's listening in on the traffic, he can just replay the traffic to regenerate the registration event, even if it's over TLS. The challenge here ensures that the registration is tied to our session, and it mitigates against those attacks. RP. This stands for relying party, like I mentioned before, the entity responsible for registering the user. What I want to point out here is the ID, which has to be a subset of the origin currently in the browser. If, for example, I'm at duosecurity.com, I try and register an RP with ID Microsoft.com, the authenticator will reject it because the origins don't match. The user. The credential will be bound to this user, just to be sure that the correct user is using the right credential. The ID is what is used to bind the credential here. Pub key cred params, this might seem a little weird, but we can essentially do here is tell the credential, or tell the authenticator, I will only accept algorithms that are like elliptic key instead of RSA. In this particular case, I'm saying, yeah, I just want elliptic key public keys, maybe for technical reasons or for security reasons. I'll talk a little more about that later. This is what it looks like in real life in a browser context. I will execute the function, and nothing will happen until I tap my blinking security key. You'll see Chrome prompt me for confirmation. I'll say allow it. And then I'll get an object called a public key credential. If we open this object up, we can see a few members. There's an ID field, which are random bytes that identify this credential. And then we'll also see in there attestation object and client data JSON. You can see this is all binary data. It's on the onus of us as developers to parse this binary data into something sensible. So I'll talk about the client data JSON and attestation object. The first represents data passed from the browser to the authenticator. The second contains the public key, which we use for authentications, the certificate, which we can use to prove that the authenticator is legit, and a bunch of other stuff. So we can first talk about client data JSON. Let's look at how we would meaningfully parse it. It's provided to us as an array of unsigned 8-bit integers, so we can use the built-in text decoder to convert it to a string, and then we parse that out as a JSON object. This is pretty simple. And then we get an object that looks like this. We get the challenge that was passed in, we get the origin, we get the type. All of this needs to be validated on the server, so I won't talk about it too much now. But for example, the challenge on the server, we would want to verify that it is the same as the one that we passed into the authenticator to prevent that replay attack. The attestation object. This is a pretty complex object that includes data encoded in a number of ways. This is a diagram of what the object looks like in the spec itself. What we can look at first is the attested credential data, which contains the credential public key down there. And we can go through the exercise of parsing this object to see how we can get to the public key. So we're going to begin decoding this object by using something called CBOR. CBOR stands for Concise Binary Object Representation. You can think of it as an advanced JSON decoder. It allows us to do more advanced things with binary data, for example. So I'm going to decode it, and then I will get a human-readable object somewhat, containing a few members, containing, if I read it out, attestation statement and authenticator data. So the authenticator data contains my public key. I'll come back to the attestation statement later. We have the SIG and X5C member. So let's take a look at the authenticator data. So we have to enter the world of byte slicing now. As front-end developers, we generally don't deal with this unless we're doing stuff with like WebGL or something. But we have to deal with things like variable length data, which the credential ID is variable length. So the spec helpfully provides something called the credential ID length field. We essentially convert two 8-bit integers into a 16-bit integer to get the credential ID length. And then we can slice the string if we wanted, or the byte string, to get the credential ID. But what we really want is after that. The public key exists after the credential ID to the very end of the string. And then we would CBOR decode that out of the buffer. And this is what it looks like in the browser console. So we have these bytes that represent the public key. And then we're going to decode that. And then we will get, like, what the hell is this, right? It's just a bunch of numbers, 1, 2, 3, -7. It's more stuff that, like, we quite don't understand, some binary data. The reason it looks like this is because this is encoded in something called COS, which is a very concise way to represent a public key and everything you need to do to use it. This, for example, says that the public key type is elliptic curve. The signature algorithm used is elliptic curve using SHA-256. The curve type is P256. You need an X coordinate and a Y coordinate here. This is all the stuff you need to conduct authentications with, and this is stuff we will use on the server later. So the attestation process, remember, it is a way to cryptographically prove that the key pair came from secure hardware. So again, we have the SIG and X5C member. X5C stands for X509 certificate, which we use all the time. Every time you connect to an HTTPS website, there is typically an exchange of an X509 certificate containing a public key, which is used to set up an encrypted channel. I will not go too much into detail about how you would verify the attestation because it would happen on the server, but you can essentially use the certificate to verify against the public key that yes, it did indeed come from secure hardware. So at this point, you're done with registration. You store the username with the credential ID that was given to you along with the public key data. So at this point, I'd like to take a step back from code and talk about the problems I alluded to earlier and how web authentication can solve them. So the shared secret problem. The credential public key is not secret. Hard to create and remember. Again, it is on the onus of the authenticator to create a random and secure credential. The easy theft problem. Secure hardware on your devices, MacBooks, iPhones, smartphones, and so on. It makes credential theft quite difficult, if not impossible. The unsafe reuse problem, credentials are scoped to an origin, again, making reuse effectively difficult or impossible. The hard to secure problem on our side, because the public key is not secret, we're not at great risk of theft because it's not terribly valuable. All right, so now authentication. This is where the user proves that they own the private key that they registered with. In security terms, this is called an assertion. I assert that I own this private key. But how do they prove it? So the authenticator makes this assertion by creating something called a signature. Signing data is a mathematical operation over bytes of data that are used to prove ownership of a private key. The data includes the client data JSON, which I talked about earlier, some other data passed from the browser to the authenticator. So the signature is created, and the signature is sent to the server for verification. We use the public key that was given to us registration to verify this signature. So again, we have a function that looks a lot like the original one, except it's called get. This requests an assertion from the authenticator. This is what it will look like from our user's perspective. The API is called, which requests an authenticator like Windows Hello to authenticate the user. The user goes through the authentication flow, and after everything is verified, we log them in. So let's take a look at the code to make this happen. The challenge, again, much as before, cryptographically random bytes generated on the server. The RP, same as before. The relying party information identifies who we are. Allow credentials. This is new. This is where the browser this is where we tell the browser to contact the authenticator that we registered before. The credential ID is passed in here, and we can also specify like transports we want the authenticator to talk over, like if they can do over USB, NFC, Bluetooth, that's all possible here. And then we wait for it. So this is what it looks like in practice. I'm going to wait for an assertion here. My security key blinks, and then I will tap it. And then I get back a public key credential object again. It looks much the same as before. We have an ID, we have a response object. But if we look inside there, we will see a signature object, which contains the signature that we need to authenticate the user. So on the server side, we would go through a bunch of verification steps, and we would verify this assertion. This is all pseudocode, because cryptographic signing looks and verification looks different with different algorithms. But from a high level, you will use these bytes that are provided during authentication, and you would verify the signature over this bytes. If the verification process succeeds, the user is authenticated. And so at this point, we have fully registered and authenticated a user without using a password. So at this point, I would like to talk about some things that web authentication is not. There are lots of things worth considering with web authentication that I've learned along the way of developing with it. The first thing is that it's not forcing us to use biometrics. Users still have the option of using passwords or patterns if they're comfortable with that. The point is that we never receive a password, so we don't receive a shared secret. The second, it's not a way for you to hack someone's eyeballs or fingerprints. You are not going to receive data about a user's fingers or about their eyeballs. If you are, something is going like horribly wrong. So, like just be aware you're just going to receive assertion data. Like you need to tell your users, perhaps, comfort them that you are not going to receive, confidential data like this. It's also not forcing us to ditch password-based authentication at all. A reasonable use case is to use web authentication as a second factor, where a user inputs a password as before, but web authentication kicks in to request a second authentication event. What this does is ensures that the user really intends the authentication event to happen, in case like some hacker has stolen their password. This is known as two-factor authentication. So what does this mean for you as developers? I think the good news is that for front-end developers, the experience of integrating web authentication into a website is largely painless. There are a lot of detailed ways to interact with the API, but when it comes down to it, there are two functions you need to interact with. There is a third convenience function for telling you if the user has like a platform authenticator like Touch ID or Windows Hello built into the device, but really just two functions you have to deal with. The real complexity comes in the back-end experience. The spec outlines a 17-point procedure to verify a registration event, for example. After that, you have to go through a number of branching procedures to verify the attestation data. So I don't want to suggest that doing this is at all trivial. It's my personal hope that we'll see some well-maintained libraries be made available to handle some of these pain points in the back-end experience. From a design perspective, I think there's an even more interesting challenge, selling the idea to users that they can still be safe without passwords. Passwords are everywhere, and in our users' minds, they are synonymous with security. They are the beginning and end of the user's typical experience with internet security. The transition away from passwords, if it happens, is going to be a huge shift in the way we think about what makes a website secure. Specifically, there's a fear of biometric authenticators, and some of it's kind of justified. There's been cases of certain Android phones storing fingerprint data in an insecure way. If we're going to be using biometrics, we can use attestation data to confirm that the authenticator is legit. It's on the onus of manufacturers to do the right thing as well. Another really good question some of you might have: what happens if your device is lost or stolen? Remember, a credential is created for every website, and the credential is bound to your device. So if you lose a device, do you have to re-register at every website? Maybe. I mean, this is not a totally solved problem. Maybe you carry a backup authenticator that's used to restore your access. Maybe there's a way to restore your authenticator data into another authenticator. Not entirely a solved problem. This is arguably one of the strengths of passwords. If you lose it, it's easily revoked. Also one of the weaknesses. Perhaps the biggest persistent problem for me was the lack of immediate learning resources to figure out how to begin working with WebAuthn. This is a great GitHub repo made by 2 researchers at my company that has been really great, provides an end-to-end example of how to work with WebAuthn. I definitely suggest you check it out yourself. So I want to close out by saying I know it can be a scary world out there. There's hackers in suits. Some of them are pointing guns at computers. Some of them are punching computers. Even Santa Claus is out to get you. And I know I've talked about WebAuthn, and I know the internet can be scary, but I also want to say that I think the picture is much bigger. Security is not just a single technology. It's a constant process and discipline. It's baked into how we should design and develop our software. It's something we should always be thinking about as we evaluate and reevaluate our choices, because our users are depending on us to keep them safe. And we have a responsibility to them, whether we like it or not. We are finally at the point where we can reevaluate the ultimate need for passwords and replace it with something better. Like this says, 80% of these data breaches would have to adapt or die without passwords. And WebAuthn provides something invisible to the end user and safer for us to handle. And that's really exciting to me. On that note, I'm currently working on a full reference guide that'll provide human-readable tutorials and guidance to developers like yourselves who are interested in working with web authentication. We hope to have it up in the next few weeks. In the meantime, I'd love to hear from you about any thoughts you have. Feel free to tweet me. Also, that's my cat. That's it.
You did talk a little bit about some of the things to do with revoking and security and so on. But my favorite question here was, which speaks to some of the paranoia that people have these days, myself included. How can we make sure that people like Apple, Microsoft, and so on don't steal, share, scrape our biometric data and put it in a central server?
So is this question about what happens on the iPhone itself, on Windows Hello itself? Yeah, it's a great question. Web authentication sort of exists outside. It doesn't directly interact with the biometric data itself. It's really on the onus of the manufacturer to do the right thing. I understand that there's concerns there. Are the manufacturers doing the right thing? Are they responsibly handling your biometric data? I cannot account for them. I cannot account for manufacturers taking shortcuts with their biometric data. It's something we constantly have to be aware of. But remember, we can still request our users just interact with passwords and PINs. Biometric data is not necessarily intrinsically tied to WebAuthn.
All right. Well, we have some more questions, and if you would check online later, we'll get some more answers. Thank you very much for a great talk.
Yeah.
Much appreciated.